Do you know free vibration of a two-story shear building is its natural oscillation without external forces? Using abacus and manual calculations with the lump mass approach, you will learn the natural frequency of the structure. This involves simplifying the structure's mass distribution to key points, making calculations more manageable. By understanding its natural frequency, we gain insights crucial for seismic analysis and structural design, contributing to the overall stability and safety of the two-story structure.
Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examined life.
In this lecture, I will cover free vibration of a shear building with 2 degrees of freedom using lumped mass approach. This is the problem which I want to solve today. It is taken from Structural Dynamics by Mario Paz, and the only changing here is W1022. In the example it says W1021, but 21 section I couldn't find in any of American sections. Anyway, it's not going to affect the dimensions at all. The first dimension is the depth of the section in inches. The second is mass of the structure in pounds per foot, so it's not going to make huge difference. I'll be using US units for the first time. Steel Young's modulus is 30 into 10 raised 6, density 490 pound second square per inch power 4, gravity 386 inch per second square, and Poisson's ratio is 0.3. We're required to find out the angular frequency and frequency in hertz, and we'll compare the results obtained from abacus and manual calculations. For solving this structure manually, we will have a free body diagram by having springs and masses. So from here, we can idealize this structure as shown in this figure A, and then it can be idealized like this, with the stiffness and mass is multiplied with u1 double dot is acceleration. So the first step is to work out the mass, and which would be necessary for our numerical model as well. So we have this 100 pound per feet square. So multiply this 100 with the floor area. So floor is 30 times out of the plane dimension, which is 15. Out of the plane dimension is not visible here. The weight of wall and other structural members is 20 pounds per square foot. So here we multiply this 20 with the tributary area. So tributary area for this top bit is 5, and here it is 7.5. When we add it up, it becomes 12.5. And then we multiply it with the out of the plane dimension, which is 15. Because we have 2 of these, so that's the reason we multiplied with 2. And from here, we get weight in pounds. And when we divide this weight by 386, we get mass, which is 136. Same is the case for the second one. For the second one, we have weight, which is 50 pounds per square feet. We multiply it with the floor dimension. 30 is this dimension, and 15 is out of the plane dimension. Again, we multiply 20 with the tributary area. Now tributary area is 5 feet times out of the plane dimension is 15, and we have 2 of these, so that's why we multiplied with 2. We get this value, and when we divide this value by 386, we get 66 pounds second square per inch as M2. We'll use this M1 and M2 in our numerical modeling. These are the section sizes from a section table, and we'll use W10 into 22, W10 into 45. The key thing to note here is that we have IXX, second moment of area, 118, and second moment of area is 248, and we'll use this in manual calculations. And other dimensions, we will use them in numerical modeling. So the stiffness for this kind of shear structure is 12 EI over L cube. But because we have 2 columns over here, the stiffness is multiplied with 2. So K1 will be 12 EI over L cube times 2 EI, because we have 2 columns at each story. And K1 is the first one. So the first one is the first floor. So first floor is 15 feet high. We multiply it with E. E is 30 into 10 raised 6. And the section was 10 into 45 W section, for which I showed you earlier, which was 248. And there are 2 of them, and the length of the section is 15. I convert it into inches. We're getting this value for K1. The same is the case for K2. K2 is the second floor. I for that is 118, and the length of second floor is 10 feet. We multiplied with 12 to convert it into inches, and we get this K2. From here we write equation 1 for mass 1 and equation 2 for mass 2. I'm not going to go into details how did we obtain this, because here the key focus is numerical modeling instead of theoretical solution. But here you can have a look at the book by yourself. We have U1 defined by these equations. These are displacements and these are accelerations. When we take the second derivative of these, we obtain these values. And in a matrix formulation, we can write these equations like this. We can write these equation A1 and A2, where A1 is amplitude. And for non-trivial solution, the determinant of the coefficient of this matrix should be 0. This gives us this equation. When we put values of K1 and M1, it results in a quadratic equation. And when we solve quadratic equation, we get these two roots. And from here, we can obtain the angular frequencies. And when we convert these angular frequencies into cycles per second, we get these two values, and then corresponding natural time periods can be obtained as well. In that way, we find out the frequencies using hand calculations. And our objective here is to carry out numerical analysis and compare that numerical analysis with the manual solution. This is the first time I'll be using US units in inches, so length in inches and forces in pounds and mass in pound second square per inch. And let's see how we get on with the modeling. I'll be using these 9 steps as I've been using in my previous lectures to model this structure. First step is part where we will create geometry. I'm going to model this structure in ABAQUS. First step is part. Go to part and double click on parts. 2D planar, deformable, and wire. Because the maximum dimension is 30 feet, and if I multiply it with 12 to convert it into inches, it is 360. So I'm going to have approximate size of the grid as 1000. Click continue. And here I want to use this line element to create this frame. Click here, click here, click here, and click here. And then again, click on the line again. Click on this space here, and here, and here. And these two horizontal lines, the beams are of equal length. So I will apply this equal length constraint. Click on equal length, press shift key, select this one and select this one. Equal length has been assigned. And these two columns, they are equal length, this one and this one. So click on this column and click on this column. Shift key should be pressed. And again, press shift key, click on this column and click on this column. They are of equal length. And then I will dimension this. So the first dimension is this horizontal line. The distance is 30 feet, which means 360 inches, 360. Then I will dimension this line. This is 10 feet. 10 feet means 120 inches. And then I will dimension this column. This is 15 feet, means 180 inches. And then simply I will exit, cancel the procedure. The structure is defined. Second step is property module, where we will define materials and assign cross sections. The next step is property. So go to property, steel material, and I'm going to define the sections as well. So modulus of elasticity 30 into 10 raised 6 pound per inch square, and Poisson's ratio is 0.3. To go to mechanical, go to elastic and 30 E6 and 0.3. You would see that here I'm not defining density, and the reason is that because the masses are lumped at flow levels, there is no need to define density. But analysis is going to give me a warning that density is not defined. There are two ways. Either you define a density and reduce its quantity by 10 raised minus 4, or simply not define the density. Here I have chosen not to define the density, but it will give me warning, and I will ignore that warning. Now the material has been defined. The next thing is to define these profiles. And for defining these profiles, I have W10 into 45 and I have W10 into 22. Let's define these profiles. These are American profiles, and this is the first time I'm using pounds and inches in my videos, and my American viewers are going to be very happy. So the top column is W10 into 22, the bottom column is W10 into 45, and these are the dimensions, and I'm going to define those profiles. So go to profiles, and here firstly I will define W1022, which is this one, 10 times 22. And this is I section. So click continue. This dimension I, I'm taking it as half of the depth. Depth is 10.17, and this is going to be 5.085. And h is the depth of the section, which is 10.17. And B1 and B2, this is the width of the flange, which is 5.75, 5.75. Because the top flange and bottom flange, they are same, so that's why I'm using the same dimensions. T1 and T2, these are thicknesses of flanges. Top and bottom flanges are of same thickness, and thickness of flange is 0.36, 0.36. And T3 is thickness of web, which is 0.24. Click continue. This profile has been defined. Next profile is W10 into 45, which is this one. And again, this is I section. Continue. I is half of 10.1, which is 5.05, and h is the depth of the section, which is 10.1. At B1 and B2, they are same, which is 8.02. T1 and T2 are same, which is the thickness of flange, 0.62, 0.62. And T3 is thickness of web, which is 0.35, 0.35. Click OK. The profiles have been defined. Now I will define the sections. So first W10 into 22 section, beam, and here material is steel 0.3. Profile name is W1022. Click OK. Section has been defined. And then again another section, W1045 section, beam section, Poisson's ratio 0.3, and W1045. Both sections have been defined now. And then I will assign those sections to the model. So go to parts, and here section assignment. I'm assigning these two bottom columns W1045, and I'm assigning this beam as W1045 as well, although the beam is going to be rigid, but I will define it anyway. Click done, and section W1045, and then I will choose these top beams and columns, and I will assign it a section. So the top ones are W1022. These sections have been defined. At this point, I will assign the beam section orientation as well. Go to assign, go to beam section orientation, click here, and then press enter. Beam section orientation have been defined. Click OK. Third step is assembly module, where we will assemble all parts. The next step is assembly. Go to assembly, click on assembly, and the part has been assembled. Fourth step is step module, where we define all analysis steps and parameters. The next is step. Go to step and define a linear perturbation step, frequency, click continue. And I want first 6 eigenmodes, 6. Click OK. The step has been defined. Fifth is interaction module, where we define contact interactions and constraints. The next is interaction. So click on interaction here. I'm going to define, first of all, the reference point. So go to reference point. Make sure that you define this reference point at assembly level. If you're going to define reference point at part level, then it will just assign one reference point. The reference point, this is my first reference point, and this is my second reference point. Reference point has been assigned. Now I have to constrain these reference points with the beams. So go to constraints, and then rigid body constraint, first constraint, and here I will tie nodes, choose the beam, and tie this beam with the reference point. So reference point is the first one, and adjust nodes to center of the mass at the start of analysis. This has been tied now. The second constraint is again rigid body constraint, and here I will tie the nodes of the top beam. So this is top beam, and the reference point is the second reference point, and I will adjust the nodes at the start, and this has been tied. The next thing is to define the mass. The mass for M1, which is here, M1 is 136 pound second square per inch, and M2 is 66 pound second square per inch. So I will define these two masses. For defining these masses, I will go to assembly, and then I will go to engineering features, inertia. I will say M1. M1 was 1 point mass. This rigid reference point, click OK. M1 was 136. 136, click OK. This has been assigned. And M2 is 66. So again, click here, M2, point mass, and click this point and click done. This is 66 pounds. Click OK. The masses have been defined. Sixth is load module, where we define boundary conditions and loading. Next step is load. Here I will simply define the boundary condition. Double click on boundary condition, say fix, and initial step, displacement, rotation, continue. I will choose these 2 points, press shift and choose these 2 points, click done, and constrain everything because the bottom is fixed. Seventh is mesh module, where we define mesh size and element type. The next step is mesh. So here I will mesh at part level. First of all, I will choose element type, click done, and then I want to use quadratic element. Click continue, and then I would like to mesh the part, and here I'm using a global size of 9, and then I will click on mesh part. The part has been meshed. Eighth is job module, which we use to run and monitor analysis. The next step is job. I will define any job, say MDOF, multi-degree of freedom, and simply accept everything as default. And here I would like to, at this point, I will save the model and define the working directory. Then I will simply submit the analysis, go to monitor, and here the first thing I'm interested in is the mass. The mass of the structure, it should be equal to summation of masses. So 202, which is fine. And then I will have a look at the frequency. The first frequency is, the first 2 modes are rigid body modes, so I will ignore them. The first frequency is 1.89 and the second one is 5.22. If I have a look at the manual solution, you can see the first frequency is 1.88, the second is 5.24, which is really very close to what I obtained from ABAQUS. Ninth is visualization module, used for viewing results. Now I will go away and see the results. So go to monitor and results. Firstly, I don't want to see this title block. So go to view annotations, and I don't want to see campus. I don't want to see triad title block. Click OK. And I want to see results for first mode, which is 1.89. And I want to activate this multiple plots. And here you can see that the first mode is 1.82, but I would like to render the profiles so that I can see the results properly. Go to ODB output and render profiles by 1.5. Click OK. Now this is the first mode, and the second mode is, and this is the second mode. If you want, you can see them in 3 dimensions as well. And I would like to see its movie as well. So for the second mode, if you click on here, you can see the second mode. And I would like to see the first mode as well. So go to steps. And this was the first mode. And again, you can play its movie. In that way, ABAQUS can really model this kind of problem with multi-degrees of freedom. Thanks for watching this lecture today. If you want to have a look at the slides and modeling files, go to tinyurl.com/jqureshi abacus, and you can have a look at full playlist at this link.